Welcome back. I hope you enjoyed your lunch break and had something nice to eat. So as promised, we now continue with the next speaker who will talk about coherence, which is basically a connectivity approach. And Fiorenzo Artoni will talk about cortico-cortical coherence and cortico-muscular coherence, which allows us to assess the communication between different sites, either be cortical sites or communication between the brain and the muscles. So Fiorenzo is not joining us here, but if you have any questions related to this talk, we will make sure that they are forwarded to him and he will answer them, and the answers will be posted once the videos are permanently uploaded to the YouTube. Enjoy Fiorenzo's talk, and we see you after the coffee break.
Good morning, everybody. I'm happy to be here, even if only virtually. My name is Fiorenzo Artoni, and I'm currently working as Maître Assistant, that is a senior researcher, at the Functional Brain Mapping Laboratory in Geneva with Professor Christophe Michel. Of course, big thanks to Klaus and Uros for inviting me here today and for the opportunity to share with you a few thoughts on coherence, and especially cortico-muscular coherence. Feel free to annotate all the questions you might have and write to me directly, and I will do, of course, my best to answer all the questions you might have. Or, if you prefer, at the end of the talk, you can leave your comments and questions to the organizers, and they will send them on. So, straight into it. I've prepared for you a four-part presentation. In the first part, I will introduce the types of coherence and, of course, why we should study coherence at all. The theory behind it, which means what is coherence, how you compute cross-power spectral density and what it is, how you get wavelet coherence, and I collected a few applications to actually get the rhythmic activity of muscles, and applications on a diaphoretic patient, neurological patients, and the relationship with Parkinson's disease. I've collected also some advanced topics, or I might say open-ended questions in literature, which means can we use synergies in relation to coherence, and can we find also the best way to process EMG and EEG for extracting cortico-muscular coherence. These are still open questions, so I put them in part 4. Now, let's see with the introduction. So, you have different types of coherence, of course. There are cortico-cortical coherence, which means that you want to study the synchrony in the neural activity of different cortical brain areas. And if you try and use cortico-cortical coherence, it means that you want to study the brain's neural communication and functions at rest and during functional tasks. Also, you have cortico-muscular coherence, which means that you are interested more in the synchrony of the neural activity of different cortical brain areas, which can be captured by, of course, different techniques like EEG, MEG, ECOG, and so on, but also muscles, both during rest or during functional tasks or during control of movement. There is another type of coherence which is less known, but maybe useful all the same, which is intermuscular coherence, which aims to study the synchrony of the activity of muscles in the frequency domain, which is involved in motor control. Then, of course, let's dive into the reason why we should study coherence. Well, as you know, MoBI means investigating brain activity while participants actively move and interact with the environment. As you can see from this video that I like very much, just to do this task, which is admittedly not that simple, you need to actually get information from your vision, and you need to track your body in space, and then of course you need to determine which movement you want to do, and you have to predict the trajectories of all your limbs to actually produce the movement you want. So this translates into a full loop where you have the sensory cortex that gets the signals from the peripheral nervous muscles, and then it transmits, I would say, just to simplify, all the data to the motor cortex that actually goes into this part of the loop where you have the transmission of data through the spinal cord to the various peripheral muscles. So as MoBI is the integration between action, feedback and perception, then you can say that cortico-muscular coherence, or coherence per se, is a way to study how signal transmission works in cerebral cortex and peripheral nerves. And it's very relevant and very important, especially for MoBI. So let's dive a little bit into the theory of it. So what is coherence? So coherence is an indicator of the linear connection between two signals, and it is an extension of the Pearson's correlation coefficient in the frequency domain. And it is obtained by the normalization of the cross spectrum. As you can see here, the coherence is the absolute value to the square power of the cross-spectrum density of the signal divided by the spectrum density of the various signals, S1 and S2, which are also called autospectrums. Now, how would you calculate all of these values? Here, you can say that the power spectral density is the Fourier transform of the autocorrelation function. The autocorrelation is the convolution of a signal with itself, and you can say that the density, why it is called density, it's because it's the spectral energy distribution that can be found per unit time. So if this represents the cross correlation, then this is its Fourier transform, which is in the continuous domain, of course. Then you can call all of these expression Sxx of f, which is basically, again, the Fourier transform of the cross correlation of a signal with itself. Now, it's very easy from this to go to the actual cross spectrum density. So it's just a matter of substituting one x with a y, which is another signal. So this is the cross correlation function, and what you do is basically you do the Fourier transform of it. And the CSD, as you can call it, is what you can say the cross spectral energy distribution that can be found per unit time. Of course, there are some hypotheses that underlie this. First, you need to assume the stationarity of the signal. Then, of course, you need to determine whether you want to calculate it parametrically or non-parametrically. So, if you want parametric methods, you need to fit an autoregressive model. If you want non-parametric methods, they are, for instance, the periodogram or Fourier methods, like the Welch or maximum entropy methods. The method that I've described now, it's a Fourier method, where you transform with Fourier the cross-correlation, the autocorrelation functions. Of course, as you might know about wavelets, they have the great advantage that they can have different frequency and time in a time-frequency transformation. They have different time and frequency, I would say, sensibility, and you can use all of these advantages also when computing coherence. In fact, wavelets can be used to overcome the problems of non-stationary signals, such as, of course, surface EMG. What is a wavelet? It's an object like this one, where you have basically a Gaussian function centered at time tau, standard deviation proportional to the inverse of the frequency f, which is convoluted with a sinusoidal wave at a frequency f. What you have basically is this, and you can convolve this to your input data, and you have the wavelet transformation of it. With similar reasonings that we did in the other slides, we can get the wavelet coherence, which is the cross coherence divided by the transformation, the Fourier or the wavelet transformation of the autospectrums, of the autocorrelations of the signals. So this basically is the same formula as before, but only calculated with wavelets instead of simple Fourier transforms. Of course, there are different types of wavelets, and each has different characteristics. You can calculate this coherence using each one of them, and it will have each one will have different advantages and disadvantages, or some peculiarities. Then let's go to the applications. So this is not properly an application, but it's a work from 1994 by De Luca that is, I think, relevant because they discover that the range of motor unit firing rate is limited from 6 to 35 Hertz or up to 50 Hertz. So in this experiment, you can see that depending on the force that you want to exert with your muscles, this is in terms of percent of maximum voluntary contraction, you have a summation effect of different motor units, and you can see that more motor units are recruited. Then you can see the oscillatory nature of motor unit firing, which is very interesting, and also it's an explanation why we are in the frequency domain and not in the time domain. Then, of course, what De Luca found is that depending on the force that you give and you want, you have, of course, different firing rates. And this firing rate is not strictly linearly proportional to the maximum voluntary contraction that you do, to the force, but it's of course monotonic increasing. So you can say that voluntary muscle contraction force of the tibialis anterior, this is the muscle they studied in this study, in relation to the firing rate and frequency of different motor units, gets to a summation effect. So this is highly relevant also for cortico-muscular coherence. We have also an example of a deafferented patient where basically you can see that the patient or the subjects and the controls, what they do is trying to compensate statically some forces that they have on a manipulator, or dynamically where the forces change and they have to actually adapt the force so as to compensate the force that is given. You can see in static and dynamic conditions that, of course, in the dynamic condition, the control is a little bit poor in healthy subjects, but nothing compared to what happens with the patient. And here you can say that beta and gamma band cortico-muscular coherence can enrich the understanding of the dynamic changes of the motor system, not only in healthy subjects, but also in neurological patients. Why is that? Because of this next slide, where Patino shows that the sensory motor system is probably resonating at gamma range frequencies to actually integrate the visual and proprioceptive information and produce the appropriate motor command. As you can see, in fact, here, in the dynamic force conditions, basically the healthy subjects present significant cortico-muscular coherence at gamma bands. So this is gamma and this is beta bands. And patient instead presented no significant gamma band, CMC, during dynamic force, but only beta range, CMC, as in the static force conditions. So we might say that with cortico-muscular coherence, we are able to discriminate afferented normal subjects versus a deafferented patient. Of course, what we can also speculate, Patino says, is that proprioceptive information is mandatory in the genesis of gamma band CMC during the generation and control of dynamic forces, which is kind of obvious, but it proves the significance of the method. Then, it's interesting to see that basically the muscular force level and the movement type can affect CMC amplitude, and it has been further shown that the level of CMC increases with the strength of EMG in healthy individuals, which indicates that muscle output is dependent on CMC intensity. And if you collect some of the works, you can see that the bands that are usually significant are alpha, beta, gamma, more beta than the others, but of course in one case also theta. So these are basically the frequencies that you should study when studying cortico-muscular coherence. But then let's see an interesting application. You can use CMC to actually compare healthy controls and patients. Here you see a few works where they compared healthy and stroke patients. And for instance, Gao et al. Show that patients had lower CMC than healthy subjects. If you actually compare with cerebral palsy patients, for instance, you can say that CMC in gamma band is lower in cerebral palsy than in healthy controls. If you check with amyotrophic lateral sclerosis patients, you would see that beta band CMC can be significantly reduced in ALS patients compared to healthy controls. And of course, interestingly, stroke patients had significantly lower CMC compared with healthy subjects for the anterior deltoid and brachii muscles, for certain types of muscles. So this goes to prove that depending on the frequencies, you can actually, if you design the study well, you can actually compare controls and patients. Now let's see an example with Parkinson. Here in this study, Helwig discovered that there is a significant coherence between the cerebral cortex and the peripheral EMG activities in the alpha range, but also the frequency range of the pathological tremor. And you can see this beautiful C4, which is a contralateral to the EMG left extensor of the wrist, centered at 5 Hertz there. Of course, this is contralateral because you can see no such thing, of course, with C3. And of course, you can actually get, if you get the spectrum of the signals themselves, you can see that the C3 data has a peak in the alpha band, the C4 also, and the EMG, once it's rectified, has these overlapping 2 bands. Of course, there is the issue of the pre-processing, which is an open-ended question, but we'll talk about it in the next slides. Now, how about gait? We are talking about MoBI, so MoBI means also studying gait, studying movement. And in this article of mine of 2017, I show that there is an unidirectional brain-to-muscle control of swing phase muscles, of the muscles of the swing leg, even during stereotyped walking. Stereotyped means gait over a treadmill, for instance. Then I show that there is a descending average connectivity strength which is much stronger than the ascending one, as you can see here. Brain-to-muscle connectivity or coherence, I would say, is greater than the muscle-to-brain. Then also motor areas are significantly more involved than other non-motor areas. And of course, we can say that the cortex actively controls muscles all the time, even during stereotyped walking. And that this control is more prominent for the distal muscles, like the tibialis anterior and the bicep femoris, with respect to proximal muscles, like vastus medialis. Now, we finally reached the part where we discuss some advanced topics and address a few questions. First, can we really talk about intermuscular coherence, or should we talk about muscle synergies? So, what are muscle synergies? Muscle synergies are combinations of muscles that are thought to be active together, and by modulating their activation, it is possible to reconstruct the EMG. Similarly to what happens when you basically decompose EEG activity into independent components. So usually motor tasks are achieved by activating an appropriate set of muscles, right, depending on the task constraints of a specific movement. So the central nervous system actually plays their role in motor control because it activates each muscle, choosing both the magnitude and the time of the activation. The modelization of these with muscle synergies actually postulates that the organization of the central nervous system instead in controlling, coordinating a large number of muscles actually goes through these synergies. So that not all muscles are singularly controlled, but rather muscle synergies, which are groups of muscles that with those controls together, they make the movement that you want to do. According to this theory, basically the CNS controls a small number of muscles rather than coordinating every single muscle that is involved in a specific motor task, or I would say a muscle synergy. So this research line, I would say, is focused on the assessment of the modular organization of the central nervous system during postural balance, locomotion, or other more complex motor tasks. And of course, there are applications in clinics, robotics, and sport science. But so I must say, is intermuscular coherence really needed? Perhaps not, because you have muscle synergies. And if you know and if you see how muscle synergies are actually calculated and computed, then you see some relations, of course, with the cross-correlation functions of different signals that you use to calculate coherence. So there is a link there, a very strong link. It's important also to understand what the steps required in the field of muscle synergies extractions, because maybe we can take also some ideas on how to process EMG to actually extract cortico-muscular coherence. So in muscle synergies extraction, you go through the following steps. First, you record the EMG, and you of course need to choose the muscles. Then, of course, the results might change with different electrode types and different placement or different experimental conditions. Then you go through the EMG processing steps, which means noise filtering, EMG integration or the envelope after rectification, baseline removal, amplitude normalization, time normalization, and then you extract the synergy with one of the methods, like non-negative matrix factorization, or PCA, ICA, or factor analysis. And of course, you know all about V's, for instance, ICA. The non-negative matrix factorization, it's peculiar because it actually works on positive matrices and decomposes them into a product of two matrices that are still positive. All elements are positive. So why are these steps relevant? Because we actually don't know at which step we should stop and calculate cortico-muscular coherence or not. And for instance, there are a few works in literature that do a full wave rectification before actually computing the coherence calculation. But this is kind of an open topic still. What is full wave rectification? It's just taking the absolute value of the signal that you have. But for instance, if you have a sinusoid of a certain frequency, when you full wave rectify and then you compute the Fourier transform, then you will notice you have included a lot of harmonics. First, you doubled, of course, the frequency content of the signal, at least, but then you include all sorts of frequency in the low frequency domain. Of course, the signal is not the same as before. The spectrum of EMG changes considerably. So this is the original spectrum and this is the rectified spectrum. Is it convenient to be rectified? Yeah, because it is closer, I guess, to the frequencies that are proper of EEG activity, like alpha, beta, gamma bands. But is it really what we should do, since the EMG has all this spectrum? For certain authors it should, for certain others one shouldn't rectify. This is just an example of one step that actually needs to be verified carefully with your data before you apply this technique. Of course, we might not know if preprocessing steps alter coherence, but they for sure alter muscle synergies. In this work, I studied different ways of processing or pre-processing the data and studied what happened to the actual number of synergies that you can extract from your data, or actually what happens to the synergies themselves. And you can see that I tried the maximum voluntary contraction normalization or the normalization by the maximum amplitude of the signal. I tried different bandpass filters, 20 to 500 or 50 to 500, and different low-pass filters from 0.5 to 20 Hertz. And unfortunately, what I discovered is that the number of muscle synergies that most criteria will give you will change depending on the pre-processing that you have made. So nothing is ever simple, I would say, right? And of course, while the normalization doesn't change much, the synergies that you extract, or the bandpass for that matter, then the low-pass filter, which basically is taking the envelope of the signal, then changes things a lot. So what should you do? No idea. Or better, you should really test, all the different types of pre-processing that you can do on EEG and EMG before trying to apply EEG-EMG coherence. Now, let's go to the conclusions and a few take-home messages that I want you to have. First, I would say that the role of cortico-muscular coherence is important as a benchmark of pathologies which are not completely understood. You saw that you can differentiate healthy patients and pathological patients. Maybe aging will change also the cortico-muscular coherence, and of course the type of experiments you do. So it stands to reason that CMC is a good feature that you can use to actually track maybe or pathologies and hopefully even the rehabilitation progress of a patient. Then, of course, and this is, I think, at least for me, that I'm a methodological guy at heart, I must say, it's very important that you don't take any method to extract cortico-muscular coherence as a fait accompli or something that is, that you can just apply to your data blindly. There are a lot of methodological issues that still need to be clarified. A few of them are, as we said, EMG and EEG preprocessing, the normalization, or how to account for all the variable external factors, which are many. So take-home message is just test, and if you want to use coherence, make sure that you do it in a principled and good way. I'm sorry for not having been present for this call, but for this presentation. But again, if you have questions, just pass them on to the organizers, that they will in turn pass them on to me, or just write me an email at the email that you saw on the first slide, fiorenzo.artoni@unige.ch, and I will answer as soon as possible. And of course, again, thanks Klaus and Uros for inviting me here, and I hope to see you all some other time in person.